Let's see. I see a visitor. Cedric's here, former student, so very recently. Now you're in Kentucky, right?
I was. I'm in France.
Cool. Any other visitors? Okay. So Sergei is going to tell us our title, Zigzags.
Yes. Thank you. Good to have an excuse to discuss some physics with you guys instead of reading the news. So, well, there was a talk by Jack Donahue a couple of months ago, where he described this model, this classical model. Let me
Sergei, I cannot hear you. I don't know if it is just me.
Sorry.
Well, I hear you. I hear Josh. Can you just say something?
Kyle, I hear both of you. Do you hear us?
Fine. I hear you fine, Josh.
Okay. Okay.
So it's a bunch of particles moving on a line, and there's this potential. And visually, one can think about them a kind of beans inside of a ribbon band, well, this potential, there are interactions between nearest neighbors and interactions of this kind. So this potential which I drew there, it's zero. So it's potential. This is the distance between particles, and so it's zero when they order, like when the k's particle is on the left of k plus 1, and otherwise it's linearly growing. So basically, what happens is that, and these particles are massless. So what happens is, at early times, we have a bunch of left movers on the right, bunch of right movers on the left, sorry, and bunch of left movers on the right, and they go through each other. And pictorially, you may think about that as what's going on as they collide, that this rubber band is kind of produces zigzags like this, and then if in this situation all these particles are free, there is no force, none of them feels any force because the forces from the left and from the right are being cancelled. In this way, a zigzag is formed. Now there is a force and particles move with linear acceleration. And what you heard from Jack a few weeks ago, a couple of months ago, that this is already at the classical level, this is a Rosenian system. In particular, it's integrable, which means that if you start with a set of momenta, the particles, and they go through each other, move all these zigzagging, then at the end of the day, you like at late times, there will be a picture like this. So there will be all these particles when through each other, and the set of momenta at late times is exactly the same as the set of momenta at early times. So this is what, in context of classical mechanics, discussing classical mechanics, one way to say what integrability means. So really, nothing happened to these particles apart from the fact that they experienced some time delays. And what you heard from Jack is their classical description of the story. And what I'll tell you now is that our attempt, which appeared a couple of days ago.
I'm sorry, Sergey, can I ask a simple question since it's at the very beginning?
Sure.
Sorry, you're saying that if particle 3 is to the left of particle 2, then there's no force, right?
Right.
But in your picture, you drew a zigzag, which I thought was that situation, and then I thought you said then there's acceleration. Like that picture, 3 is the one that's your hands on right now, right? And
Right.
2
So,
is like right.
let's say this is particle 1 and this is particle 2. Let's talk about 2 particles.
But
So
then there's no force at this point, right?
No, there is, yeah, so, sorry, so the potential we should run here, that's the difference between chi qi minus qi plus 1. So, what situation we should run here corresponds to, we allocated here, so there is a force. So there will be no force if particle, or 2 particle case, if particle 1 and particle 2.
Sure. Okay. Yeah. I just had the I plus ones backwards. I thought it was minus 1. Okay. Sorry. Yeah.
Okay, thanks. So yeah, what I'll tell you today, I'll tell you about our attempt with Jack to understand quantum physics of this model. But before doing that, let me tell you a few words. Why do we care about this model? Because, well, I should say it was rather frustrating paper to write for me. It took more than 2 years, and that's probably the simplest model I ever thought about. And it was probably also the hardest paper to write. So it was. So I think it's worth spending some time to explain why do we care about this. Well, the initial motivation comes from the following. It comes from thinking about confining strings. Quantum thermodynamics. And well, basically, that's the statement that if you take 4-dimensional QCD, you take, say, fundamental and anti-fundamental quark, Q bar, where this Q has nothing to do with those Q, but that works, and those are coordinates of the particles. Because of confinement, there is an object formed between them, which is string, and well, we want to understand dynamics of the string, and there is, well, for many reasons, these are interesting and remarkable objects which are hard to understand. Let me just give you, one piece of intuition. So there is an interesting limit, and when there is any limit when this objects become really interesting, which is called Hoff limit. So if we think about QCD, this is this theory with H group S3, and so if one, there is a limit when one instead can think about H group kind of takes 3 to infinity, and so there is a long standing hope that in this theory, in this limit, theory simplifies sufficiently that one will be able to understand confinement. And what happens in this limit is that these strings, they cannot break. And not only they cannot break, so meaning that in actual physical QCD, if you start separating quark and quark pair sufficiently far apart, then eventually the length of the string will be such that the energy stored will be larger than the sum of the masses of the quark and the quark pair. And what may happen is that you form, now instead of having a single string, you form 2 pieces of string. That's what happens in real world. And that's the reason why we don't see these long string-like objects. However, if one considers theory with a large number of colors, then these effects are suppressed. And so if one kind of tries to work in the limit when one takes cross the limit of color to infinity, then one gets a situation when processes like this are impossible. And moreover, that also means when you consider kind of some interactions of two strings like that, or interaction of very long string which may self-intersect, that what happens at the processes like this, the string goes through each other without experiencing any force. So it's a very unconventional object if you think about it. So the string, it's a little bit like a shoelace. So it's a physical object, it has energy momentum. You may study kind of it wiggles, but in this limit of infinite number of colors, it's a shoelace which can go through through itself without noticing it. So that's well, that indication to some extent in this limit, we're talking about what's called should be properly called fundamental strings rather than some.
Can you give an explanation from the Hamiltonian why? You might think they would just get stuck on each other or something, even though they can't break, but you might think they couldn't pass.
Well, but that's a.
I know you're telling us that's true, but can you kind of explain so we can understand why?
Well, it basically happens from studying the property of interactions gauge theory in the top limit. It's a thing.
You're saying it over and over. Can you give us an intuition why that would be the case?
Well, actually, I don't have good intuition to be honest. Well, the intuition is that from kind of just studying the diagrams in doing some diagrammatic in gauge theory, we realize that in this limit theory reduces to string theory with number of colors playing the role of string coupling. So we get this way we get strings with zero string coupling, which tells us that that's what happens, that when the string goes through each other, it doesn't notice it's present. But well, yeah, I don't know, maybe, but yeah, to be honest, I don't have good intuition, and that's part of the reason why it's kind of so mysterious this object. But maybe, well, roughly speaking, what happens is the following. So I'm not sure that's perfectly good intuition, but still, so yeah, we have this fundamental and anti-fundamental force, and they charge under chromoelectric force, and kind of for them to form a color singlet. Well, in some sense, kind of in this line which I'm drawing here, there is a sum over all possible colors which connects to them, and so and basically, as they cross each other, yeah, you need to make, in some sense, to kind of for something like this to happen, for instance, for string to intersect like that, you need to have like some infinite number of in the n to infinity limit. You need to have some infinite number of kind of color reconnections, and but yeah, I'm not sure.
Maybe another way to ask questions. I thought I had an intuition sort of about why you don't make a pair,
Right.
but that seems quite different than they're actually going through each other instead of just like bouncing off or something. But
Well, yeah,
my
but
intuition was probably wrong about why they don't form a pair.
well, but I think, well, if you have an intuition of why they don't have a pair, I think the second step is easier to make, because well, at the end of the day, these strings, we're talking about Lorentz invariant theory, right? So
Right.
all excitations, all like hadrons in QCD, they're made up of the strings, right? So, and in Lorentz invariant theory, in relativistic theory, it's impossible to have, if there are elastic interactions, necessarily there are processes, because of crossing symmetry, there are necessarily processes with particle production. So somehow, so maybe that's kind of one way. Well, again, if you think you have an intuition for the absence of pairs, that's more or less that, combined with the fact that it all happens in Lorentz invariant theory, that implies that also there is no room for any elastic interactions.
They're equally mysterious.
Right.
Okay.
I mean,
Well,
one thing
Yeah.
One thing that I had wondered is to the extent that you have like, 3 3 colors and, 3 times 3 is 9 and you get 8 gluons and 1 singlet, and the limit of like n squared minus 1, that minus 1 is kind of, the 1 is irrelevant when you go to large n, but I don't know if, that seems relevant to the story about color singlets and things, but it's not quite an intuitive picture either. I just mean if you, and the kind of young tableau of it all, the color singlet that you get, when n goes large is sort of seems like it's something weird is happening there.
Yeah.
You're maybe saying of all the different Q-bar pairs you might make, almost all of them have the wrong color to leave you with 2 color singlet. That was
Yeah.
kind of the underlying intuition I had, why I wasn't so bothered about it's not breaking. But I can't see how that translates. Interrupt you.
Okay. So, well, what is the relation of this to this? Well, actually, this model was derived. We arrived at this model as an attempt to understand exactly this physics in a somewhat simpler situation. So we're studying not 4-dimensional QCD, but 2-dimensional QCD with adjoint quarks. And so in 2-dimensional QCD, there are no dynamical gluons. And so these objects, these particles, which you have inserted inside the string, you should think about them as adjoint quarks. And there, also in 2 dimensions, the understanding confinement on its own is not that hard, because if you have just 2 electric charges, then there is a linear force between them. So confinement is a classical phenomenon there. But so when one now studies, so one may still study dynamics of a string in the presence of these adjoint quarks, and kind of this theory arises at their leading high energy approximation to dynamics of confining strings in 2-dimensional QCD. But actually, I don't think. Well, I think this is one of those cases where I think going to 2 dimensions, you're not losing that much, because both in 4-dimensional QCD and in 2-dimensional QCD, at the end of the day, we're trying to understand the dynamics of 1-dimensional object of a string. And kind of I want to think about this more, coming back to 4 dimensions, then you may think about these particles as really being like gluons, because that's the adjoints which we have in 4 dimensions. But kind of what I meant to say, so that's not just a toy model of these dynamics, but in some situation, it's really arises as a leading node approximation to this kind of dynamics at high energies. Okay, so well, that was our initial motivation, but there are many other reasons why this model is actually quite amusing. And let me mention just maybe one of them, which will be quite important later on. This is an unusual example of interacting n-body system where n is finite, and this n. Sorry, I should. So this n has nothing to do with the number of colors. So this is just a number of particles in the system. So this is example of a n-body system which is Lorentz invariant, namely just at the classical level. So I wrote for you Hamiltonian, and clearly this system has also conserved momentum. The sum of the momentum of all these particles, and one can write yet another function, which is by this expression. Doesn't matter that much the explicit expression, but it's is there, which is very simple. And the point is that at the level of classical Poisson brackets, this quantity J P and H, they form a two-dimensional Poincare algebra. So that's example of a canonical system with which at the classical level is invariant on the Poincare algebra. And well, this is something which is quite unconventional. And actually, when we read quantum field theory textbooks, we will often hear that, well, the quantum mechanics plus Poincare symmetry implies quantum field theory. And the usual argument for that is kind of in terms of thinking about single particle dynamics. So if you're just trying to quantize free particle, then there are problems and to quantize it in conventional way, preserving causality without introducing multi-particle states. But actually, well, there is another side of the argument, which has nothing to do with quantum dynamics, but which has, it's a classical statement about Hamiltonian mechanics. And it has nothing to do with free particles. But it's the statement which was kind of known since late 60s under the name of no interactions theorem. And this is the statement that if you want to have finite dimensional canonical Hamiltonian system with this property, and it has Lorentz symmetry built in it at the level of classical plus one brackets, that all systems like that can be, by change of variables, essentially by redefining momenta without touching coordinates, can be reduced to free systems. And so, in some sense, that's even more basic. So so really it's not quantum mechanics plus Lorentz invariance implies we need to do quantum field theory, which is a system of infinite number of degrees of freedom, but really kind of Hamiltonian classical dynamics plus Lorentz invariance, plus if you want to get an interactive theory, that's already implies that the theory is free, but that's all only true in dimensions 3 and higher. And so and this is a counterexample which is possible in 1 + 1 dimensions, but still kind of it's amusing to play with a system like that and to see how it behaves. So that's maybe more general situation.
So just be sure I followed all that.
Yeah.
This is an example of an interacting quantum mechanical Lorentz invariant system.
With finite dimensional phase space, right? Already at the classical level. This is something very unusual. Okay, and now, so from Jack, you had a description, I think, of a very nice story of understanding integrability of the system at arbitrary number of particles. So we constructed a full set of integrals of motion, actually, there are n integrals which are +1 commute with each other, and 2 n-1 independent integrals, which the maximum number which you may have. So today I'll tell you a few words about our success or progress in trying to quantize the system. And I should say, well, we succeeded, but I think the most interesting part is not how it worked out. Well, it's interesting, but probably I also won't have time to really fully cover it. But the reason why it turns out to be very hard, and why some simplest attempts don't work. So, and for these purposes, and for the rest of my talk, I really will focus just on the two-dimensional version of the system. So that really explains what I said at the beginning. So it's hard to think about simpler physical system like that. So, right? So it's a system of just two particles interacting with this Hamiltonian. So it's two massless particles on a line interacting with this potential. Well, if you take in quantum mechanics 1 and somebody writes to you this Hamiltonian, you may think that you would know how to quantize it, right? So let's follow Dirac and promote Q's and P's into operators, canonical commutation relations inherited from Poisson brackets. So it's one may be slightly concerned by the fact that we're talking about massless particles here, massless relativistic particles. So this kinetic term may look somewhat unconventional, but on the other hand, at first sight there is nothing wrong. So this operator, square root of absolute value of p. So we work, for instance, in the coordinate representation. So we kind of have function psi of q. Then in the Fourier space, operator absolute value of p can be defined perfectly fine. And well, there is a one gets this expression at the end of the day. So dq pi to the e times this is psi acting on absolute value of p acting on psi of q can be defined this way. So q prime psi of q prime times principal value of q minus q prime squared, where principal value is just same as 1/2 of pole in this integral, and the principal value prescription corresponds to drawing a contour which goes above the pole, below the pole, and taking 1/2 of the sum. And kind of the way to derive it is just take function psi of q.
So is there an extreme, I mean, what's the deal with the K? Or,
Sorry,
D to the IP. Q minus Q.
no, sorry, I should, yeah, I messed up here. Sorry, thank you. No, it just is, right?
okay,
I skipped one step. Yeah. So what I was going to say that, yeah, the way to derive kind of that was a reference to how one derives it. That one starts with a function psi of q in the coordinate representation. One takes Fourier transform, multiplies by absolute value of p, the Fourier transform, and then makes Fourier transform back. And as a result, it's straightforward to check that one gets this expression, and so
And in this expression, also the absolute value is important, right? It's not just so.
well,
is
this
square
expression
root of
gives the
square.
definition of, that's an actual definition of operator absolute value of p, right? Or in principal value.
No, I mean the absolute value. So that's the square root of p square, right? And we just two determinations.
Well, it's, you can call it principal absolute square root of p squared, and we call it absolute value of p.
And that gives the principal value,
All right. Yes.
not any other way to go around the poles.
Right, but also, well, if you think about it, there are not that many because you want to get the Hermitian operator, so it's hard to think about something else, but principal value. Yeah, so then with this definition, it sounds like, again, if you are taking one-to-one, then you know what to do, right? So you write this Schrödinger equation. So plus psi of q. And well, it's a little bit unconventional looking equation because it's not local in Q. There is its integral equation, but otherwise it's perfectly tractable integral equation to solve. So that looks like okay. This is the way. That's maybe the way to quantize this area. Well, and it is a quantization of this area, but it's not the quantization which we like, and which not the quantization which I like, which now is correct one. And there are several ways to understand it. So there are several indications that something is wrong with this procedure. So one indication is that let's come back to our initial model. So I'm studying these two particles. And in this model, to start with, at the classical level, there are actually three different sectors. So one sector is that to start with, I have two particles, they move in the same direction. Both are right mover. So remember, that was potential. And what I wrote here, I wrote already kind of the Schrödinger equation for the difference. I went to relative coordinates. And, I decoupled the overall motion of this. So if I start with initial conditions such that my both P1 and P2 are positive, or both P1 and P2 are negative, so I'll call these two sectors kind of left, or right. Then classically, these two particles will never interact because they always move with the speed of light, so they will just keep moving freely, and that will stay forever. And on the other hand, if I start from situation like this, then the zigzag forms and dynamics, which I was talking about, so you realize this. So at the level of classical dynamics, there are these three sectors which one finds in the theory, and the existence of the sectors, which was quite very important in our analysis of the classical dynamics of the theory, particularly when one goes to classical integrability of the theory. When one goes to n particle cases, similarly there are n different subsectors corresponding to the number of left movers and right movers. And now this quantization, it's completely it completely loses the structure because if you think about what this right sector is, well, this is a sector where one simultaneously have the following. One has the P1 and P2 are positive, and P1 is smaller than Q2. So one imposes, that's the definition of that's what they call, I think, right sector, right? So these are two particles which always move right. And then it's straightforward to check that at the quantum level, so there are no functions like this. So you try to construct in the coordinate representation, for instance, functions which satisfy this property, namely that, well, functions of Q1 and Q2, which are only non-zero when Q1 minus Q2 is negative, and which they have only positive Fourier components. That there are no functions like that, basically because of uncertainty principle. Because imposing simultaneously these two conditions, one would respond to trying to restrict both momenta and coordinates of the particles, and that's important. So that's already, that's impossible. So that's already indication that something goes wrong. We're losing something when we're trying to perform this this quantization. But there's yet another reason, but I don't have time to go into detail why we didn't like it. But perhaps the main reason is the following. So if one takes these expressions for, some miracle I didn't erase them. So when I have this, take this expression for JP and Q, JP, H, which I wrote for you, and tries now to calculate the commutators, then one finds that the Poincare algebra doesn't close anymore at the quantum level. So this Poincare symmetry, which we liked, which was interesting at the classical level, is lost at the quantum level as a result of this quantization, and it doesn't like there are some contact terms essentially coming from when one tries to there's some ordering ambiguities which appear here, and when one tries to calculate commutators, there will be some contact terms, and it doesn't look like there is a way to come up with ordering prescription which would restore Poincare symmetry. And so that's the real reason why we don't like this quantization. That it well, it looks like it's anomalous. It breaks Poincare symmetry. But it would be nice to understand what's going on. Apart from this technical argument that okay, you try to calculate commutators and they don't come out right. It's nice to draw a picture which explains this why this happens. And so let me try to draw this picture. Yes.
So are you saying the quantization is inconsistent, or you just don't like the fact that you break the Lorentz symmetry?
Yeah, it definitely describes a well-to-do quantum system, but just this quantum system is not Poincare invariant, it's not Lorentz invariant, right? So that's well, and also there's a side remark. It also breaks integrability, which kind of we wanted to preserve, but that's what I think breaking of Poincare symmetry is kind of more fundamental problem, right? So so that's what's really wrong about this quantization of physical ground.
Because that would mean it's no longer a good model of your.
Well, for instance, yeah, it's not because okay, coming back to kind of the motivation, what we hoped for, we hope to use, as I said, this kind of Hamiltonian arises at kind of as a describing leading dynamics at high energies on confining strings. So what we're trying to like one goal of this whole program is to solve that leading high energy dynamics and then develop perturbation theory around that approximation, some high energy approximation for dynamics inside the confining string. But of course, on the way you break Lorentz invariance, that can be a good description of confining strings in relativistic theory. But also from the kind of the motivation which I mentioned, the system on its own is interesting because it's an example of finite dimensional Lorentz invariance theory, interaction theory. Well, if you break Lorentz symmetry at the quantum level, then this motivation also disappears. So yeah, let me try to explain to you, and let I provide to you some technical reasons. So we tried to calculate commutators between these operators, and we didn't find a way to define those operators such that commutators satisfy Poincare algebra. But let me draw for you a picture which explains why it didn't. Why we failed. So what I draw, I'll do the following. So, well, let me spell out kind of what I did more explicitly what I did when I went from here to here. So I really, as I said, one separates the kind of center of mass of overall motion from relative motion. So this is total momentum, that's conjugate coordinate, which is just average coordinate of two forks, and let's introduce relative momentum, which is difference between two momenta. And so this Hamiltonian, which I this Schrödinger equation, which I wrote for you, that's a Schrödinger equation where I already factored out motion, overall motion of the particles, and just look at the relative coordinates. So let's do the following. Let's draw. Let's fix the just classically. Let's fix the value of total momentum, and let's look at the geometry of the phase space in the PQ plane. So namely, let's just draw the lines of the Hamiltonian flow, which describes this. And so for for it here. So for say P positive, the picture will be the following. So this is P, this is Q. So this is capital P over 2. This is minus capital P over 2. And so I told for you that there are these two sectors here, and they correspond to two different regions in the phase space, namely. So here there will be, that's what we would call right sector, where that corresponds to exactly to this configuration like shown here, that the difference of coordinates between particles is negative and they both have positive momenta. And so here in this plane, the Hamiltonian flow actually is 0. So because for particles, when they're here, they just move as a overall, but their relative coordinates don't change, and so relative momenta don't change. So the Hamiltonian flow completely vanishes here. On the other hand, the complement of this in this plane, that's what corresponds to this left-right sector, and the phase trajectories they take some form like this. So also you start from here, time to minus infinity. You are here, and then they freely move for a while. At this point, zigzag is formed, and then particles like this zigzag unfolds, and then particles come back and they exchange their momentum. So this is the set of phase trajectories, and at t smaller than 0, the picture will be the same, but instead of right, one would have left sector here. Now the point is that we see that already at the level of classical theory, this Hamiltonian flow is it's badly discontinuous on the boundaries between different sectors. So there are some non-smoothness here, but that one might think that one may smooth this out. But what happens when one approaches this boundary, then really there is no way to say the dynamics in this part of phase space is in any way continuation of dynamics in this because here one always stays the same. Really, the flow, the Hamiltonian flow itself is inconsistent. In other words, the message here that when one says, well, it's already seen at the level of Hamiltonian flow, it's also seen, of course, at the level of boost operator. So if one thinks how boost operator acts, then boost operator in the left-right sector, when you apply a boost, you may change the value of momentum, positive momentum into negative momentum, right? So you switch. So you can, by applying sufficiently large boost, you go from here to negative momentum. While on the other hand, when you act on two right movers, they always will just redshift, and they always stay right movers. So what I'm trying to say that already, so classically, when I told you that there is this G, P, and H act on the phase space, well, really, they don't act on the full phase space, but you should cut out this boundaries between different topological sectors. So somehow, in thinking about quantization of this model, and well, maybe it's also interactive. Draw what happens at equal to 0. So if equal to 0, there are no left to right move. So this is E. So the phase trajectories look like this. So they go like this. Continuation of the picture. So this is total P equal to 0. But as you can see, there is kind of bad discontinuity along the line little p equal to 0. So the Hamiltonian flow goes in opposite direction there. So kind of and that explains what happened, what went wrong with this quantization. So this quantization, the straightforward quantization by Dirac, it completely it neglected this fact that the real phase space, we insist on already classically, we insist on thinking about this as a Poincare invariant theory, that our phase space is not like P1, P2, P1, P2, but it's like these three different sectors, and the boundaries between different sectors, they should really be cut out from the phase space.
Sergei,
Yes.
is it possible another way to think about this? I guess Massimo was suggesting is to look at like a French cover over this. Yeah, and really kind of think about this cuts as French cuts.
You mean in the definition of this?
Because you're taking the square roots. And
Yeah, I don't know, maybe, yeah, I'm not sure.
because in the study of the Misch model, this kind of the French cover of the.
But here, kind of, I'm saying that already at the classical level. So, and the message here that in quantizing the system, already at the classical level, one kind of strictly want to think about what is the Hamiltonian dynamics here. It's not it's not defined on the full four-dimensional space, and it's defined really on like three different subregions of that space. And so, in quantizing and carefully quantizing the system, one should think about, worry about this non-trivial geometry of the phase space, which completely neglected by standard Dirac quantization.
But it could be that there's a well-defined phase space in like on the cover, just when you do the projection, you have this cuts. Because these are on different sheets. The region in RR and the region beyond RR, they're on different sheets.
So I think maybe there is a way to extend.
That's right.
Yeah, but still it will be something non-trivial, right? So,
Yes.
Yeah. Yeah. No. Maybe there is. Well, indeed, as I said, we managed to quantize it, but so far the quantization which we have is by far. Well, I think it's correct, but it's somehow by far less nice and less elegant than the story one finds at the classical level. So,
Yeah, the reason I mentioned that is because like people, when they study the spectral curve and stuff, they treat this Hamiltonian as essentially the definition of some, elliptic or hyperelliptic curve. That's going to be the cover of planar phase space.
yeah, well, maybe there is. Yeah, I hope there is some better language like this. But well, in the remaining like 10 minutes, let me tell you how we managed. Like we didn't not in a nice language like that, but we did it somewhat more straightforwardly. But let me still tell what we did to quantize the system. And well, so lesson number one, that so kind of one should remember about this dynamics, the trivial phase space geometry. One should think separately. Probably the most straightforward way, just to think separately about these three different sectors: right, left, and left. So right, and left, they look somewhat trivial, although even there it's slightly non-trivial. But yeah, one spend time, I don't want to go there. But there, okay, you have just two free massless particles, right? So on a half line. So that's what can be simpler than that. So let's not spend time on that. So let's discuss how to quantize the system in the left-right sector. Well, at zero total momentum. So again, the main lesson here that one needs to kind of remember that one quantizing not the full plane, but one quantizing the plane with that half axis being excised. Well, and to do that, in this case, it's rather straightforward. So one can build coordinates which kind of provide global, which cover this region, which is the physical region, and these coordinates, they are defined. Well, I'm sure all of you remember Jack's talk. So we just defined action angle coordinates there, and those coordinates they provide indeed global coordinates on kind of the physical part of the phase space. Well, but basically, it's something like roughly speaking, is the following. So there's these different trajectories, and so you may choose, you may label every point by, say, the initial momentum, by where, how far this trajectory starts from the axis in the vertical direction, and by the time which it takes, well, by the time along the trajectory. And because dynamics here is very simple, so particles move, like all evolution here is piecewise linear functions of time, all dependence of P and Q. So one can really solve this very explicitly. And let me write for you. Well, maybe. Oh, no, I think I can write. So, so if one goes from what I had before, from P, Q, and P and Q bar, so these were initial set of coordinates. If one goes to set of coordinates defined by these somewhat complicated looking expressions, minus this, and there is so basically my new coordinates, they're labeled by Q bar and, well, actually H and P. And so, and for instance, the initial Q is related to new Q in this way, and there is seemingly transparent and nice relation, but for Q bar,
What's in the denominator under the absolute in the first line? That's a Y or a?
no, this is four.
Oh, sorry.
This is 4, this is 2.
Okay, thank you.
No, it's, yeah, there is no unusual symbols in there. So basically the statement is that there is a canonical change of coordinates from these guys to these, where I wrote for you like one of the explicit relations between initial Q and final coordinates. And in this new, with the following property. So first of all, these new coordinates, they have property that they cover with the restriction that H should be positive. It is. It's a Hamiltonian. So it's literally Hamiltonian. So these new coordinates they provide a global one-to-one parameterization of the physical part of the phase space. And in these coordinates, my system really looks like a system of just two particles. Well, yeah, I shouldn't have written it. It's better to say that there is some. Well, it was better to write it in slightly different. In new coordinates, one really just finds two massless particles. One can explicitly write it, go into half sum and half difference of H and P. Then one finds that in new coordinates, my system is just a system of three massless particles on a line. So it looks straightforward to solve this system then. And basically the way one solves it, one constructs a set of wave functions labeled by H and B by total momentum and total energy. And there are three massless particles on a line, so there is no question that that quantization preserves Poincare symmetry. However, well, it all looks completely free. So one may wonder, okay, where did all dynamics went to? Well, dynamics went into the statement that, well, actually, to talk about physical observables, I now need to recall. So I constructed Hilbert space by going to these three variables, but I need to use my initial physical coordinates to interpret dynamics in this system. So it's not that conventional, actually. In classical mechanics, it's locally every system by Darboux theorem, every system can be written just a system of free particles. So it's really, we kind of usually don't notice it, but really already at the level of conventional quantum mechanics, it's all dynamics in some sense is the choice of coordinates. But here it's just being made very explicit, and also it holds not just locally but globally in the phase space. So to properly now interpret physics of the system, what we need to do, so we have, in other words, we have wave functions which are directly, let me set p equal to 0. Then I kind of work directly into energy representation, because kind of in this quantization I construct wave functions which are just functions of h. On the other hand, I have this somewhat complicated looking expression for my, so that should be physical coordinate operator. It looks a little bit complicated. It somewhat simplifies in the rest frame. And so what one needs to do in the rest frame, say if one wants to study fine scattering phase shift, one solves the following equation. One solves the equation. Oh, let me write it here. So what it did here is the following. So it's kind of, it's the opposite of what we usually do in quantum mechanics. Usually we start from, say, coordinate representation. We start with psi of q, and then we write, say, we go to stationary scattering theory. Then we solve the equation right like this, right? Then we solve the equation that q psi is an eigenfunction of the Hamiltonian, and we're solving stationary Schrödinger equation. So here I already started in the basis. My quantization naturally led me into the basis of Hamiltonian eigenstates. So what I'm looking for now eigenfunctions of the physical coordinate operator, which is defined in this way, which is somewhat complicated operator, but at least in the rest frame, there's a natural way to define it. So this integral part here came for similar reason as I explained in the beginning, trying to define those absolute value to appear here. So in other words, this equation is just equation of this kind. Is that I'm looking now. I'm solving this equation, but note that kind of, so we can call this psi sub h of q, and here we can call this guy psi sub q of h. But these two things are the same object, right? So these are they define, these are matrix elements between q and h eigenstate. So I can solve it this way, or I can solve it this way, and if I succeeded doing it, then I have, just for the purpose of say describing this matrix, both approaches are equally well. But also there is extra bonus which one is getting here, namely, if we want to study scattering angle, then we want to take q to infinity limit, right? That's where well, when we look at our wave function to deduce the scattering, And for the point of view, this equation corresponds to semi-classical approximation. So somehow, if I'm interested in studying the S matrix, then automatically in this formulation, one ends up being solving semi-classical problem, even though that will produce exact quantum answer. But it's just because for determining S matrix, one needs to go at long distances. And in this representation, long distance corresponds to semi-classical limit. So yeah, I'm run out of time, but I just conclude saying that, well, with Jack, we managed to solve this equation in the Q to infinity limit, deduced from the S matrix, which kind of correspond to, well, that was initial motivation also why the system is interesting, because at the classical level, the time delay which one gets from this scattering, this corresponds to what the system which was studied quite a bit recently. Stefan, I guess they were talking about that, was called TT-bar deformation. So it's a time delay which proportional to the energy collision of the particle. And so what one finds here, because essentially of this semi-classical property, that this time delay is exactly the same at the quantum level. So this n particle subsystem provides a quantum mechanical system which can reproduces n particle subsector of TT-bar deform series. I'm cheating a little bit when I'm saying that. I don't have time to go into that. But also, this is a very amusing, it's very amusing way to quantize this system. It's kind of, instead of solving Schrödinger equation, and one starts here from energy eigenstates and one talks about instead like looks for eigenvalues of Q operator, or introduce physical coordinate operator, which I think is interesting for several reasons. But yeah, let me pause here.
I have a quick one. But I asked one. Somebody else go first. So it looks like you're left with an equation that sort of isn't soluble, obviously, but your original dynamics were at least very specific and clear. So can you actually solve that equation for psi sub q of h and find a formula for it?
Well, there's no way. Yeah, I'm not aware. I don't think it's.
Or some, what's it like? I mean, would you like to use Mathematica?
No, numeric. One can solve it numerically.
Right. And so what's it like?
I don't think it's solvable exactly analytically. It's solvable, as I said, we managed to solve it at Q to infinity limit. One can solve it and can deduce the exact S matrix. It's also, there is a pre-limit. If one kind of one thinks this potential which I had, if one reproduces dimensionality here, then actually there is a dimensional like tension of a string appears in front of this term, right? So that's kind of the coupling constant in this system. So the pre-limit corresponds to, instead of talking potential like this, corresponds to the introducing potential which is kind of hard-wall scattering. And here it would correspond to dropping this term. So in this limit, this equation can be solved exactly. And actually that was important for us to get also, because to do semi-classics, one should do some matching. So it was important for us that we were able to do it. Away from there, yeah, I don't think it can be, well, this we don't know how to solve it exactly, but first of all, it's not guaranteed when you start from exactly solvable classical system. It's not guaranteed that you will be able to solve everything in the resulting quantum model. So this quantization, when one goes to n particle, generalize it to n particle case, is still an integrable model. It provides integrable definition of quantization of this model. But essentially, the question is to what extent. So the level of S matrix, we know exact S matrix, but you're asking whether we know kind of off-shell dynamics of this model, how kind of we can really solve for wave functions in the intermediate times. And
for example, what's its asymptotic dependence of the cross-section on energy or something or
no,
other?
no, S matrix we know. No question about the same.
What kind of a theory is it in the end? It's not a trivial one. It's not.
No, yeah. So yeah, I said it by words, but yeah. So right there, but it's what kind of called TT bar deformations. So, but
Maybe I should, maybe this is.
but this is just
technical for a minute.
it's a full NS matrix. So if you have two particles, well then statement as a result, like, let's say this is left mover and this is right mover, then this is matrix, it's multiplied then by factor like this. And there is so at the level of scattering, that's all what happens. So the states multiplied by factors like this, which tells us that, well, actually, there is some funny, it's not TT bar would be this, but in these models there is some funny constant prefactor here. So it's not exactly TT bar, it's almost TT bar, but kind of that's a little bit more subtle. But in the zero-dot approximation, it's the same as this, which physics of it is that there is a time delay which is proportional to the momentum of the particles. So it's exactly kind of what one would guess from looking at the zigzag picture. And otherwise, nothing happens. There is no particle production. So from that point of view, that's a good news for us because we wanted to use this model as a zero-dot approximation for some perturbation theory. And so we see that there is a way to quantize it in such a way that it kind of there's nothing happens, which is good. Almost nothing happens, which is good. But whether one can solve this equation away from this asymptotic limit for other observables, not the kind of scattering amplitudes, that's unclear, and that's again related to many questions which I have about those that kind of theories where they really have well-defined off-shell observables. And I suspect that the answer is no, but that's a separate issue. But this for some observables, for most immediate physical observables we may care about, but for scattering amplitudes, yeah, there is exact solution.
Questions?
Just quick question. So what does the next correction look like? In the string scale? And do you expect it also to preserve integrability, or do you think there's already going to be lost at the next?
No, first of all, I don't expect to preserve integrability.
Already at the next order.
And to be honest, yeah, I don't know because that's part of the problem. So this quantization, even though it's not very friendly for developing perturbation theory around it, but at least I can tell you my expectation. And that's something also we're working with further, and Sasha will care. But the expectation is the following: that well, if you look at this zigzag, even classically, if you look at this dynamics, as you grow energy higher and higher, there is this long period when there is this two endpoints move with acceleration, and so there is this like long semi-classical regional space is being created. So the expectation is that there should be, so this process should give rise to some copious production of soft particles, and that's what we're trying to calculate. So that's the expectation is that will be the next correction, which makes sense both from the point of view in QCD strings. You expect that there will be lots of soft particles produced in the processes like that, but also from the point of view, that's something which I didn't tell at all, but well, it's related to what it started with, right? So this dynamics of QCD strings, why it's interesting in large N limit, because it describes dynamics of geometric objects. It describes dynamics of two-dimensional dynamical geometry. And so there is expectation that these dynamics should be possible to reformulate with some two-dimensional theory of gravity. And this zigzag would correspond to some kind of black hole. And from that point of view, it's also natural to expect that there should be some copious production of particles. So that's kind of what we expect. I don't know the answer yet.
So thanks, Sergei, again. Wolfenstein chapter. And,
So fun, Sergei.
Thank you.
Usually one always